Hello and welcome to the Moldflow Research and Development Update for 2020. My name's Franco Costa and I lead the team of Autodesk developers who work on enhancing the Moldflow solvers. In this presentation, I'm going to show you some of the things we've been working on. But before I do that, I need to explain that what I'm showing you are things that we hope to bring to you in the future. However, today, I'm not making any promises regarding exactly when or in what form these enhancements will take. So you should not make any purchasing decisions based on what you see in this presentation. So the topics I'm going to cover in this presentation will include some new features that we hope to deliver in the upcoming commercial release. These are enhancements regarding visual quality, accuracy of shrink and warp predictions, a new feature of automatic packing, chemical foaming, and some other enhancements. I'll also touch on some features which are in technology preview. And finally, I'll show you one or two things that we are currently working on for long-term development. So let's get started by looking at some new developments in the area of visual defects. The first area I want to look at is the prediction of sink marks in complex 3D geometries. The current method that we have available is limited to only finding sink marks under ribs, but we've been working on a new method which considers all geometry. As in this example, we can see that the underside of this part has a number of 3D shapes and ribs under the curved surface. If we look at the result in 2019, we're not able to predict the sink marks all through the part, whereas the new version predicts sink marks everywhere where there are ribs on the other side, and also some 3D chunky regions. As a validation of this sink mark prediction, I want to show you some results we have from our laboratory. We molded a plaque using an ASA material, and this plaque has on the underside ribs of varying thickness, 1, 2, and 3 millimeters. And we've taken a laser scan of the sink mark's depth. And moldings and samples were collected for a range of different packing pressures all the way up to 80 megapascals, so that we could see the influence of packing pressure on reducing sink mark depth. So here's a comparison of those measured sink mark depths and the predictions. We see on the left the results for the 1 millimeter narrow rib. Shown in blue are the measured sink marks from the molded samples. Orange is the original sink mark prediction, and grey is the new sink mark prediction, which more closely follows the trend and magnitude of the measured samples. Similarly, on the right, you can see the results for the 3 millimeter thick rib, which is the one furthest from the gate, and we can see that the sink mark depth is higher, being further from the gate. And once again, the new prediction is a better match for the trend of the measured sink mark depths from the molded samples. The other enhancement for the prediction of visual defects is a new way to view the Birefringence results, which is called a fringe plot. A fringe plot is similar to what you would see if you viewed a transparent part which has Birefringence effects in polarized light, for example when using a pair of cross-polarized filters. Each light and dark band represents the retardation of light by a wavelength of the particular light color. The more bands that you see, it means the greater the retardation, and in fact, the greater the stress level in the part. In the example shown in the upper image, a pair of polycarbonate lenses have been molded and a Birefringence analysis performed. And that Birefringence result is now examined using this new fringe plot property with the shaded light and dark bands representing stress levels. In the lower image, the same parts have then been overmolded with a frame. And notice that the overmolding introduces additional stresses in the warpage and in the Birefringence result. So we see a different pattern of banded light and dark shades in the overmolded sample, representing a higher stress level there. The next topic I will discuss are improvements to shrinkage and warpage prediction, which are targeted for the next commercial release. The first of these topics is that we have introduced a method of considering crystallization effects to enhance the accuracy of prediction of 3D shrinkage and warpage. As many of you know, semicrystalline polymers undergo a sharp drop in their specific volume as they're cooling through the solidification temperature or the transition temperature. We can see this clearly in the PVT diagram of many semicrystalline materials. For many years, we've had a proprietary treatment in our midplane and dual domain solvers, which captures this effect and allows for an accurate shrinkage prediction. The same treatment has now been implemented in our 3D solvers. The benefit of this is that for semicrystalline materials, we now expect to have more accurate shrinkage and warpage predictions for our 3D solutions, and also better consistency in the volumetric shrinkage and in the deflection predictions when you compare midplane or dual domain results to 3D results. I'm going to now show you a comparison of these predictions to measured shrinkage outcomes on the shrinkage molding tags that we mold in our laboratory. These are actually the plaques that we mold to take our shrinkage measurements for to develop our CRIMS coefficients for midplane and dual domain. But here in this example, I'm just using that original molding data as a validation for our 3D prediction. There's no correction being performed using the shrinkage data. These shrinkage tag moldings are done at a range of different processing conditions, 25 conditions in total. And these are spanning over 3 molding thicknesses, 2 mm, 1.5 mm, and 3 mm, and also different packing pressure levels, different melt temperature and mold temperature levels, and different flow rate levels. In this first example shown on the left, a 20% talc-filled polypropylene has been molded, and here I'm showing you the measured shrinkage in the flow direction in the blue line over the 25 molding conditions. As you can see, the shrinkage ranges from about 0.6 to 0.8%. Also shown is the prediction from the 3D solver in Moldflow Insight 2019 Update 5. And you can see that the prediction is quite a lot lower than the measured shrinkage values. Now, if we add to this the prediction from the new solution, which includes this enhanced crystallization effect, we see a much better agreement in the magnitude of shrinkage, being in closer agreement with the measured values. I can also add to this the prediction from the dual domain solver, and you see that the new solution in 3D is also more closely matching the solution prediction from the dual domain solver. It's worth mentioning at this point that this new enhanced crystallization effect will typically increase the shrinkage predictions for those semicrystalline materials which are sensitive to this effect. Let me stress, not all semicrystalline materials will be showing this effect, but the ones that are affected by this change will typically show an increased shrinkage prediction. Now we can look at a second material, in this case, an unfilled PBT material. Again, we're looking at the measured shrinkages shown in blue in the flow direction, and these average around 1.5%. Shown also are the predicted shrinkages from the 3D solver in Moldflow Insight 2019 Update 5. And you can see that they're already higher than the measured values. When we add to this the new prediction with the enhanced crystallization effect, we actually see that the overprediction has increased somewhat. Again, I stress not all materials will show this increase, but here I've picked out 2 materials where the increase is strongest. As a comparison, I can also show, again, the dual domain shrinkage prediction, which was closer to the measured experimental shrinkage values. Neither of these materials has strong anisotropy effects because they're not reinforced by any fiber filler. So the predictions and the measured values in the transverse direction are quite similar to the ones that I've shown here in the flow direction. So I'm not showing those transverse comparisons to you today. What I do want to show is the effect that this crystallization effect has on simulation results. In particular, let's compare the volumetric shrinkage. Here we see a comparison of the 3D prediction in Moldflow Insight 2019 on the left, a dual domain prediction in the center, and the new 3D result on the right. Now this part has various thick and chunky regions which are not particularly well suited for solution with dual domain. So I'm going to limit my comparison to the areas of uniform wall thickness where dual domain and 3D are doing a reasonably similar job. And we can see that the volumetric shrinkage result, here we're looking at average volumetric shrinkage in 3D, which represents a total volumetric shrinkage effect through the thickness in the local area, and comparing that to the volumetric shrinkage result in dual domain, which also is a total volumetric effect through the thickness of the part. And what we can see is that the new 3D result has numerical values of magnitude of volumetric shrinkage which match more closely with those of dual domain, whereas the previous 3D result from 2019 did not have such good agreement. Likewise, we can also compare the deflection results for those 3 simulation cases on this part. And again, we see that the new 3D result has a similar magnitude of deflection as the dual domain prediction, and both are higher than the previous 3D result. So this is an example, as I said, of reducing the differences between predictions from our 3D solver and the predictions from our midplane or dual domain solvers. Now, I'd like to turn our attention to the prediction of mechanical properties in composites, in either with fiber reinforcement or other types of filler content reinforcement. Of course, these mechanical properties influence and have a contributing factor to the warpage deflection predictions. So we've made a change to the way we decompose matrix properties for composite materials where we assume isotropic matrix properties. And this is actually the case for most thermoplastic and thermoset materials. We typically assume an isotropic polymer matrix property, and we estimate those properties by examining the measured composite properties. We've made a change to the way we do that decomposition to more accurately derive values for Poisson's ratio, modulus, and coefficient of thermal expansion. For most materials, there is no significant change, but there is a change for some materials. And this change was already introduced for 3D solutions in the Moldflow Insight 2019 Update 5 release because it had a significant effect on the warpage prediction in 3D. However, we did not make that change yet in midplane and dual domain, and we will be bringing in the change of this decomposition accuracy improvement for midplane and dual domain in our next commercial release. The reason we delayed the change for midplane and dual domain is twofold. Firstly, those changed quantities did not have a big effect on the warpage prediction in midplane and dual domain. But also, if we had have done that, it would have required us to recalibrate all of the Crim's coefficients, and this was a process that we had scheduled to do for the next major commercial release, which is why we delayed the change in decomposition. If you look in Moldflow Insight 2019 Update 5, and you compare the estimation of matrix properties from a 3D solution to those from a midplane or dual domain solution, you will in fact sometimes notice this difference, with some slight differences in estimated values depending on geometry type. Here's a comparison for a 35% glass-filled PA66 material of the modulus, Poisson's ratio, and coefficient of thermal expansion, which resulted previously, say from Moldflow 2019 Update 2, to the new corrected values. The modulus and the Poisson's ratio are only changed slightly. But the property which is changed strongly in this case for this material was the matrix coefficient of thermal expansion estimation. Notice that the corrected value is approximately 4 times higher than that which was previously estimated. And this would have a large impact on the magnitude of warpage deflection predictions in 3D analyses. If we compare these estimated values to the values for pure unreinforced PA66 materials, we see that the corrected value is actually more typical of the coefficient of thermal expansion that we should expect from a polyamide 6,6. A second change to Micromechanics calculation for composite properties concerns an improvement we've made to the calculation using the Mori-Tanaka model for anisotropic polymer matrices. This is typically used for LCP materials where we cannot assume isotropy in the polymer matrix. The change only applies to those composites which have disc-type fillers, that is, an aspect ratio less than 1. What we had realized was that the accuracy of the Mori-Tanaka calculation could be improved for cases where the aspect ratio was less than 1. As an example and a comparison here, we're showing a verification done comparing the numerical micromechanics values of modulus from the Tandon-Weng model and the Mori-Tanaka model. The Tandon-Weng model is the model that we use when we assume isotropic matrix properties, and it allows an exact calculation. The Mori-Tanaka model is being used here in the case of isotropic matrix properties in order to evaluate its performance over a range of different aspect ratios in comparison to the Tandem-Weng model. You see that the aspect ratio ranges from around 30 to values below 1. And we see that the comparison between the Tandem-Weng and the Mori-Tanaka model deviated in 2019 at aspect ratios less than 1. However, with the new improvement, there's better agreement with the Mori-Tanaka model now agreeing with the Tandem-Weng model. The next improvement I'd like to outline for you is the handling of insert-to-insert contact during our 3D warp calculation. This is where we have adhesion between multiple inserts now being handled. Previously, in Moldflow Insight 2019, if an insert was in contact with another insert, that contact interface was not considered during the warp calculation, and the inserts could move apart. In this example shown here, there are two inserts shown in grey and in yellow, and a moulded cavity which is shown in green. In the Moldflow Insight 2019 result, we see that the yellow insert has not moved. It's remained stationary and has a deflection value of 0, even though the insert which it was in contact with has moved up and should have also forced the yellow insert to move up. If we look at the lower image, which is the prediction from the new version, we see here that the two inserts remain in contact with each other. This enhancement of insert-insert contact has been successfully applied in the case of mesh aggregation and also to analyses not using mesh aggregation. The final enhancement that I'll show you today in the area of shrinkage and warpage is an improvement to the 3D buckling prediction, as this has now been enhanced to allow mesh aggregation algorithm to be used. The mesh aggregation algorithm is a strategy we use to speed up the calculation of deflection results in 3D, rather than doing the structural finite element analysis on the full flow analysis mesh. We use a simplified mesh with reduced numbers of elements. Previously, it was not able to use this mesh aggregation strategy for 3D buckling, but recently we've made enhancements to the quality of the mesh aggregation, the mesh structure in fact, produced for the mesh aggregation. And this allows us to use mesh aggregation now also during the buckling analysis. A comparison here is shown of two analyses. The first was performed without mesh aggregation, and the second was performed with mesh aggregation. These are both buckling analyses, and the eigenvalues predicted are similar. However, notice that the solution time is greatly reduced by a factor of almost 10 here, and also the memory required is reduced. This will have a significant benefit when you're analyzing the buckling analysis of very large models. I can also mention that this new improved mesh aggregation structure, which has slightly less elements than the previous method, means that there's also a slightly faster solution outcome when using mesh aggregation for small deflection analyses also. The next enhancement I wish to show you is the addition of an automatic packing capability. This automatic packing capability allows us to estimate a suitable packing pressure and packing time based on the material characteristics of compressibility and the pressure required to fill the part. This new feature will be available in both Moldflow Insight and Moldflow Advisor. Although it will not yet be the default method, we may make it the default method after we've received some feedback about how effective the method is. What the method does is that it seeks to minimize the shrinkage in the part while staying well within machine pressure limits. As an example, I'm going to show you now the interface for this automatic packing in Moldflow Advisor. What you see is that the traditional packing profile input, which takes an 80% level of the filling pressure required to fill the part by default. So if we look at a part example here, we can see that in this case, the injection pressure was barely over 1 megapascal. So if we look at the packing profile that would have been used for this, the packing pressure was around 1 megapascal. This is not going to be enough to have a well-packed part, obviously. Now, if we turn on the new automatic packing profile feature, there's no longer the table where you enter the duration and packing pressure level. In this case, the packing pressure level which was used was something around 28 megapascals. And if we compare the warpage deflection predictions of these two analyses, the one on the left, which used 80% of filling pressure, and the one on the right, which used the automatic packing profile, we see that the amount of deflection has been reduced. Now, of course, if you have exact molding conditions, if you have already molded parts and you know what the packing pressure profile was, then it's always best to enter the exact process details. But if your design is at an early design stage, you do not yet know how the part will be processed, you do not know what the suitable packing pressure is, and you're just trying to gain an idea about how the part will perform and what its shrinkage will be, it may be that the automatic packing profile is a more reasonable estimate for you than using 80% of the filling pressure. Next, I will discuss enhancements to foam injection molding. The first of these is introduction of microcellular injection molding capabilities for reactive materials. This is quite similar to the microcellular injection molding for thermoplastic materials that has been available in our software for many years, but now it's available for thermoset materials. The other new process which is introduced is a chemical foam molding, which we expect will commonly be used for polyurethane foam molding. But it can also be used for general chemical blowing agent reactions of other types. What's unique about this process is that the foaming gas is generated during the molding, so that the reaction is generating the foaming gas in the cavity rather than the foaming gas being generated in the barrel of the injection molding machine, as is the case for other foaming processes. So that means that we need to track the reaction kinetics of the foam generation reaction, as well as the reaction kinetics of the curing reaction of the thermoset material. So in this new process, both reaction kinetics are independently being calculated. Specifically, we have the gelling reaction, which is the thermoset curing reaction, which here is represented as the chemical equation for the polyurethane, but also the blowing reaction of isocyanate and water and urea, which is generating the gas which causes the bubbles of the foaming reaction. But if it's not a polyurethane that you're molding, you can specify the nature of the chemical reaction of some other blowing agent, if that's appropriate for your process. The first example that I will show of chemical foam molding is an example where the initial injection volume is only 2.5% of the cavity volume, and the rest of the cavity filling is driven by the foaming of the polyurethane. And here we see the fill time result initially, and then after foaming, the cavity is being filled, and there's temperature results and density results, and also pressure results as you'd expect. So in this example, we can also verify that the temperature evolution and the density evolution are in accordance with measured values coming from an experiment reported by BASA. 4 experiments were done with different levels of water concentration, and in each case we see that the evolution of temperature due to heat generated by the reaction and a decrease in density due to the foaming are well matched in our simulation. A second molding example, which comes from work published by Mitani, compares the flow front advancement of an experiment and our simulation here. This cavity being filled has 2 thicknesses. On the left is a 35 mm thick region, and on the right is a 65 mm thick region. So the flow will advance differently according to the different thicknesses. And we see that pattern in a photograph of the molding experiment and also of the simulation. As is common in polyurethane molding, the injection position is at the bottom of the cavity where the unfoamed polymer is first introduced, and then the foaming causes it to rise and fill the cavity. Next, we'll look at some other improvements that we are hoping to deliver in the forthcoming commercial release. The first of these concerns the Solver API enhancements which have been made. I'll remind you that the Solver API is an open framework for external researchers to enhance the calculations being done in our 3D Flow and Warp Solver. Up to date, there are existing capabilities for users to code their own viscosity, PVT, solidification, and core shift functions, which allow them to model different processes or different materials than what are normally handled by our solvers. Now, what we've been working to introduce in our next commercial release is a new general purpose convection capability for any user calculated quantities. For example, one of the quantities that you might like to calculate is a degree of crystallization or a thermal degradation effect. Any such quantity, either of these or something else, that you insert into the calculation will be carried forward with the flow of material automatically for you. So you only need to implement functions which describe the reaction rate and initial conditions, of course, but you do not need to also calculate the convection with the flow of these quantities. Now, as an example here, we have a kind of prototype code which we can share, which implements a Nakamura crystallization model. And we can see from this the degree of crystallization which is predicted by this model, with the skin layer having low crystallization because it cooled very rapidly before the crystals could grow. And also the density variations that occur due to this crystallization. Another new capability being introduced is the option to do your own fiber orientation calculation. We know that there are a number of researchers who are interested in implementing alternative fiber orientation models and wanting to see their effect on mechanical property prediction and on warp prediction. And this is now possible in our development code. I should mention that the fiber orientation itself is a quantity that's being convected by the previous method that I described. Other enhancements to the Solver API capabilities include to allow you to access the powder concentration result at each node, if you want to use that in a modified viscosity function, for example. Also to allow you to access the average fiber length result at each node, if you want to, for example, use that in a fiber orientation model. And we've also introduced utility functions which allow you to identify what material is being molded. And lastly, we've done an enhancement to allow the control of the time step size during the flow analysis and to allow the control of the injection speed and packing pressure control during a flow analysis. And this we had done to allow integrations with models of molding machine behavior, which were being developed by an injection molding machine manufacturer. Another enhancement is an improvement we've made to the prediction of weld surfaces compared to the predictions in 2019. In 2019, it was often the case that the weld surface would be quite a broken surface. There were gaps in it. And we've made an improvement to that so that now a more continuous weld surface is predicted, which is useful for the prediction of weld strength using the Helios AME product. Other improvements that have been made to the solvers include some improvements to the optimization solvers. And the optimization solvers I'm talking about are automatic injection time, runner balance, and molding window, which rely on a simplification of the geometry model to do a flow estimation. And this flow estimation algorithm has been improved to better capture temperature and shear rate effects. We've made improvements to the meshing of surfaces. We've made improvements to remove the incidences of high aspect ratio elements on curved surfaces. We've also been working to improve the stability of the numerical calculations in all the solvers, removing instances of small random variations in results, and also working to minimize the differences between different computers, so we have more consistent results regardless of what hardware the analysis is run on. There have been some significant improvements to the stability and time step control of analyses where valve gates are included, particularly at the time when the valve gates open, and there can be quite a almost explosive flow rate and very high shear rates, and we need to control the analysis at that point with very fine small time steps to capture those effects. There have been improvements to the calculation of barrel compression effects for the midplane and dual domain solver, to more closely agree with actual molding experiments and to more closely agree with what's already been implemented previously in the 3D flow solver. There have been some improvements to the calculation of powder and fiber concentration, avoiding some instances of spurious spikes in the values of those quantities. We've added the RAM position as an output result in the screen output and also in XY plots, so that you can view the progression of RAM position during injection and packing phases. And there have been some improvements made to the wall slip calculation so that it's correctly handled during compression molding analyses also. Everything I've discussed up to this point are features that we are hoping to include in the next commercial release. As well as this, we're continuing our program of technology previews where we are seeking your feedback to drive improvements in some prototype features that we have been working on. And alongside the next commercial release, we hope to also continue the availability of these technology previews. The first of these previews that I'll mention is a shrinkage correction method for 3D. It's not actually the CRIMS method, which we use in midplane and dual domain. It's a different method based on adjusting or calibrating the coefficient of thermal expansions. And in the technology preview presently, this is only available for non-fiber grades. That is, for grades which have isotropic shrinkage properties. I'll show you an example here of an unfilled PPT material, the same one that I'd shown earlier regarding crystallization effects. And again, we're looking at the flow direction shrinkage. And you had already seen the measured values, which are shown in dark blue, the prediction from Moldflow Insight 2019, and the new prediction, which included the crystallization effects. In addition here, in light blue, you can see the updated prediction where we've used the shrinkage calibrated coefficient of thermal expansion. And as we would expect, this brings the predictions quite close to the measured flow direction shrinkages. We can look also at the second material that I had shown earlier, the polypropylene with 20% talc fill. And again, we're looking at the shrinkages in the flow direction over the 25 molding conditions. However, this time you see the introduction in light blue of the enhanced shrinkage prediction using the shrinkage calibrated coefficient of thermal expansion. And this time, strangely, the prediction is actually lower than the measured values. So I guess this is a sign that this feature, although promising in some materials, still requires more work in others, which explains why we haven't put it yet into the commercial release. Another technology preview feature, which we'll be continuing, is the deformation analysis with assembly constraints. This is an option for a 3D warp analysis and allows you to apply constraints at assembly mounting points. This capability is already available in our commercial releases, but what's not available is to adjust the position of those constraints according to the mold shrinkage allowance. And this is important if you want to correctly model where those constraints actually are and what influence they're going to have on the warp shape. And this was a top requested enhancement from some previous user group meetings. So in the technology preview feature, you see this option which allows you to calculate the final deformation after assembly and nominate what was the shrinkage allowance factor in the mold dimensions. And here we see an example of this feature being used in an analysis of an assembly of a door panel, courtesy of Chang'an Auto. Another technology preview feature which we are continuing is an option for the 3D warp analysis where we consider the stress relaxation which occurs while the polymer is still constrained in the mold. And this uses a 3D anisotropic thermo-viscoelastic residual stress model, where the viscoelastic properties are characterized by a generalized Maxwell model. And the time-temperature superposition, which requires a temperature shift factor, can use either tabulated shift data, the WLF equation, or an Arrhenius equation. The aim of this stress relaxation method is to better capture the effects which occur due to different cooling times in the mold. In the example shown here, we have a short cooling time of 6 seconds and a long cooling time of 60 seconds. And what you notice is that the warp result is different, with higher warpage in the molding which was held in the mold for less time. In the case of the longer cooling time, where the cooling has occurred in the mold, constrained by the mold, the stresses have relaxed while they've been constrained in the mold at elevated temperatures, and this then results in lower deformations once ejected from the mold. Another technology preview feature being continued is an option for 3D Warp to consider that the shrinkage which occurs in the thickness direction will be higher than the in-plane directions due to the mold restraint effects. And we have seen some success in improving deformation predictions with this feature. For example, in this molding, which was done in our laboratory, it's a box-shaped mold, and the sides of the box bow inwards due to temperature differences on the inner and outer mold halves. And we see an improved prediction when we use the residual stress model coupled with this thickness shrinkage scheme. Another continuing technology preview feature, not yet ready for commercial release, is the prototype prediction of tiger stripes. In fact, what we're predicting here is the onset of the flow front instability, which is a factor in the presence of tiger stripes. However, what we are not currently considering is whether this instability leads to visual effects. This is because the visual effects depend on the presence of fillers and the orientation of those fillers due to the flow front instability. We're still seeking validation studies from industrial partners to help improve the robustness of this prediction. What this feature does is it gives a result showing the flow front instability threshold, and in regions where this flow front instability is high, depicts the areas of potential tiger stripes. Tiger stripes is a name given to a phenomena of visual defects where there's alternating bands of high and low gloss regions. However, it depends on which angle you're viewing these from, which bands appear high and low. And it's all to do with altered reflections due to the presence of fillers. So as I said, these areas of high potential visual defect are only potential regions depending on what fillers are present. Lastly, I'll mention some areas that we have under long-term development. And these are definitely not going to be included in the next commercial release. So I mentioned the topic of shrinkage correction in 3D and that we were working on a calibrated coefficient of thermal expansion, which was available in technology preview for non-fiber filled materials. Well, of course, we are currently now working to extend that method to also fiber filled materials. And it's more complex here because we need to apply the correction not just at a composite level, but also at a component level. So here I'm showing a comparison of prediction for a glass-filled polycarbonate material, showing both the flow direction shrinkage on the left and the transverse shrinkage on the right, which are very different in this material, given that it contains glass fiber filler. And you see in blue, the darker blue, the measured shrinkage values, again from the same shrinkage tag moldings done in our laboratory. And you can see a prediction of shrinkage predicted by the standard residual stress model, and also a prediction of shrinkage coming from this shrinkage correction method, the shrinkage calibrated coefficient of thermal expansion. At the moment, we're exploring a number of different possible model implementations of this idea, and one of them is shown here, that for this material showed some promising results. Although, if you look at the flow direction shrinkage, I guess there's not much to look at. The difference between the measured value, the value predicted by the standard residual stress model, and the shrinkage values predicted by the shrinkage-corrected CTE method are not very different. However, where you do see a strong influence is in the transverse shrinkage predictions, where the predictions using the standard residual stress model in the commercial software are quite distant from the measured values, over-predicting by more than a factor of 2. Whereas the shrinkage predictions in the transverse direction obtained using this shrinkage correction method, calibrating the coefficient of thermal expansion, are in much better agreement with the measured values. Another long-term development we're working on is to improve our 3D meshing functions. I mentioned previously some improvements to the surface meshing, but we're also working on improving areas where the 3D meshing introduces large elements that are inappropriately large compared to the surrounding mesh. And a few examples of these problem areas are shown here on the screen. The other aspect of the 3D meshing that we're seeking to improve is to upgrade the 3D mesher, which is present in the Moldflow Advisor software, to bring it up to an equivalent level of the Moldflow Insight mesher in terms of aspect ratios, dihedral angles, and obtaining the desired numbers of layers through the thickness of the part. So there you have it. In an upcoming commercial release, we're hoping to deliver features which allow you to inspect the visual quality of your parts. We have to have improvements of shrinkage and warpage predictions, a new feature of automatic packing, a new feature of chemical foaming, including polyurethane foaming, and other enhancements and improvements to the solvers. And in a forthcoming technology preview, we'll continue with some new options for 3D warp prediction accuracy, and tiger stripe prediction. And in the long term, we're working to bring shrinkage calibration also to fiber-filled parts. I hope you've enjoyed this presentation